Move on to slicing and slicing software. Okay, so previously we discussed splitting a 3D model into the different layers to be 3D printed, and we've slightly touched upon slicing software, but what is it actually? So between having your 3D model created, where you have the 3D CAD data of what you actually want to 3D print, and 3D printing it, there is an intermediate step because, as we mentioned, 3D printers work in a layer by layer method, and your 3D model needs to be split in that layer by layer, method for the 3D printer to be able to read and actually understand the cross section of each layer and what it needs to print or what it needs to create for each layer. Okay, so the splitting of a 3D CAD model into these different layers to be printed, that's what slicing is. There are several programs that are specifically dedicated or created for the purpose of slicing. Some are free, some are paid, some come with and are specifically designed for certain 3D printers by certain brands. But the main thing that they have in common is splitting the 3D model in all of these different layers that we need. So as an example, I'll show you one 3D slicer software that I mainly use. However, let's prepare a 3D model for us to print. If we go back, we can export this model of the table or the chair that we wish to 3D print. You can go into File, Save As, and then if we call this, okay, let's call it Design 1. We have to save it as a specific file type, and we'll cover this later on when we discuss file types. But for now, all you need to know is when you save 3D models for the specific purpose of 3D printing, you need to save them in an STL format because that's what generally slicer softwares use or read in order to slice a specific model. Okay, so now that we've exported it, we can go into our 3D slicing software. This is a Repetier host, but there are several different slicing softwares out there. This is just the one that I'm using for this example. So let us add a model in here. Design1.stl, open. So you can see over here, when we imported our design, it sort of laid it face down, obviously because it tries to give us as much contact area with the build face as is possible. We can obviously rotate the object around axes. You have a set of axes as you do in Ansys SpaceClaim. This is generally standard in most 3D printing software. We can rotate it around. For this specific example, for me to show you some of the features, we'll pretend we want to build this table, the right way up, with the bottom facing the bottom and the top of the table facing the top. Although how it was previously orientated with the top facing the bottom and the bottom facing the top would have been better because you wouldn't have needed support structures, but let's go with it right now for this example. Over here we can set different settings such as the infill, what filament that we are using, the different temperature, the speed we wish to 3D print it at. But we'll just go with some standard defaults over here, just for this example. Over here, as you can see, with some of the presets that I've set, it's automatically created a little brim for me because of the tiny surface area that's in contact with the build plate. Yeah. So obviously in some of the settings that I've set over there previously, in some of the presets, you can give it a brim and it will automatically do this for you. However, what I can show you over here is the different layers. I can show you the first layer, the second layer that it builds, and how it actually works progressively to build up all of the layers and all of the cross section through the slicing software. Now, if I reach the main body of the table, you can see that here throughout some of the layers, it doesn't fully fill it up. You can see this is sort of the cross section. Yeah, this is the infill that we specified. Obviously, for some of the layers previously before that, it fills it in completely just to give us a strong base. But then as we progressively go up, it sort of skips a bit just to give us that infill percentage. I believe the settings that I have over here are 10% infill, but then when it gets to the last few layers, it auto completes it to give us a smooth surface area over there. So over here, you can see the print settings that I put are 10% infill with a fast speed and a brim. Can add, okay, let's put 10% infill with a few supports. Supports. Let's see if this adds some supports for us to actually see how they look like. Well, so let's go, because we still have it set to layer 80. Now, if we go up, you can see that it's sort of encapsulated inside a box. What this box is over here is the actual supports that we used for the top layer, for the overhangs and features. Support the structure. If we go back to layer 0 and work our way from there, you can see it builds the supports straight on the bottom, yeah, with our legs as it gets started. And as we go up, it builds a little supporting structure around what we're printing, right? Obviously, it doesn't use a lot of material, and it leaves a bit of a gap between our actual model and the support structures. This helps with removing the support structures later on using post-processing. But all of these are settings that you can play around with, you can change, and they will depend and vary depending on what equipment you're using, what 3D printing technology you're using, and what material you're using. So there's no set standard for these. You have to play around. There's different, let's say, presets that you can use, but there's always room for improvement and efficiency gains. All right, so obviously that's just a quick inside look on support structures in slicing software. But as I mentioned, there are many features that you can edit and change, certain parameters that you can also change. Over here, you can see there's a perimeter. This is to clean the nozzle head, and it's another thing that you can set. Sometimes if you are using a multiple nozzle extruder, you'd have an extrusion tower to purge the nozzle between filament changes. There's many different things that you can play around with, but the more you delve into this technology, the more complicated it can get. And these are really advanced topics that are beyond the scope of this course that we're currently discussing. But anyways, this is just a quick insight, a quick look into slicing software. Obviously, I'm not going to cover it in depth because this course is mainly focused on Ansys SpaceClaim and 3D modeling. The intermediary step with slicing, that's dependent on the slicing software and the 3D printing technology that you're using. So it's a broad topic, too broad to be covered right now in this course, which is just a general overview. But let's see what we've discussed. Okay, so we've discussed that it's an intermediary step between the 3D CAD model, and the 3D printer. How the slicing software splits the CAD model into the different layers. There are numerous programs. Okay. So you can input the different parameters into the slicing software like print speed, layer thickness, material properties, infill, temperature of the printed head, many different parameters. You would need a whole separate course just to cover slicing software in itself. This is just a basic overview. Okay, last but not least, what we're going to cover are the different file types that we'll encounter during 3D printing. So pretty much if you look over here on the right, you can see the 3D printing flowchart where you start with a design, a conceptual design that you might have in your head or that you came up with for a specific purpose. Then going from the design to actually creating the 3D CAD model representation of your design. Once that's finished, you send that off to be sliced in the slicing software, and the slicing software actually outputs a code that your 3D printer can use and can read to actually physically print your model. After you finish printing, you can go back and iterate, going back to the design, making design changes, reflecting that in the 3D CAD model, and so on and so forth. So pretty much what we have here is obviously once we have our model in SpaceClaim, generally what we want to save it as when we click Save As, you have several different file types over here. Generally, if you want to work on it a bit more, you save a copy as a SpaceClaim file or SCDoc. That allows you to open it in SpaceClaim and edit it, and it has the structure tree and most of the changes that you've built and most of the geometry captured. However, if you want to send this part off to be 3D printed or off to be sliced more so than to be 3D printed, generally you'd save it as an STL file. STL is standardized triangular language. So what it does is, obviously we'll go into a bit of theory here. As an example, when you draw a cylinder or a sphere, obviously there are no corners, there's rounded faces. And these rounded faces, they're generally defined by a constant involving pi. If you've ever done some mathematics involving circles, spheres, or area defined by a circle, you'd encounter the mathematical constant of pi, which generally rounded up is 3.14, but it's an irrational number. That means it actually goes on to infinity. So it's actually 3.1415, etc., 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 indefinitely. It doesn't actually have an end. And obviously, as a mathematical constant, this program can calculate that, but when you send it off to the 3D printer, slicing it and actually conceptualizing this can create a lot of problems from a memory or a RAM perspective for the computer. So what we do in this case, we export our 3D model as an STL, standardized triangular language. And what that does is it breaks up the geometry into many little triangular faces that make up the geometry. So this circle will actually be split up into line segments that would form triangles on the face of the model. And this helps save a lot of memory, and it helps actually compress the files. If we actually look at one file over here, that's as not an STL, but as a SpaceClaim file doc. Let's see how big that file would be generally. Okay, so let's see the properties of this. You can see it's around 6 times larger. Obviously, this is a very simple design, so we're still speaking of kilobytes, but you know, converting it to STL can save a lot of memory or space, you know, up to 6 times in this example. And that's generally the file type that slicing software can more easily understand. Some other file types that you might encounter when 3D modeling that are usually posted online, just generic 3D file types are OBJ, STP, PRT, WRL. These are just different file types that have their own specifics, but you can import them into Ansys SpaceClaim and edit them that way. If I go back into Ansys SpaceClaim, let's try to close this design that we have, and let's try to open our STL that we saved. So we go from SpaceClaim files, let's go into STL over here, and let's try to import design 1. You see, this is a good example. So obviously, considering STL is standardized triangular language, you can see all the different triangles that form up the face, that broke up the face of the circle. Obviously, this is what the slicing software understands, and this is how it sort of mathematically simplified the circle, getting rid of that pi constant and irrational numbers and some other complicated mathematics that went on over there. Simplified. But obviously, you can import the files in SpaceClaim and you can work on them and do all sorts of things. So let's see. Obviously, we've covered that you generally just slice STL files, so you need to convert and export your data. Yes. So let's go back into our slicing software. So let's say that we've finished, we've decided that yes, this is the code that we want to generate for our 3D printer to print. You can save this code or export it onto an SD card, and that way it's portable. You can carry that with you and the 3D printer can read the code off of that SD, or you can send it online via web using Wi-Fi 3D, real-time 3D printing. You can even edit the code that will generate. So you can see over here, if I go into G-code editor, so G-code is actually what slicing software produces, is what most 3D printers read and understand. You can see that you have obviously some parameters over here. These listed in green are comments generated by the software. This is not actually part of the code. This is to help you reading the code if you actually want to go in and edit code lines itself to optimize some of your 3D printing. You can see I've added the skirt, which is this boundary over here. Some of the temperatures, disabling some cooling fans over there, setting them, and it gives you all of the X, Y, and Z position and how much to extrude for each layer and the area. So all of these, it gives the 3D printer the exact coordinates and how much material to extrude at those coordinates while it's building your object or your target 3D model. And you can see it's really long. Over here, just for the simple table, 100 layers, you have around 28,000 lines of code, roughly. So there's some clever logic going on over here. There's some optimization, some automation. Obviously, if we are to write this code by ourselves, writing 28,000 lines of code is quite tedious and time consuming, drawing up the path for everything that the nozzle head should follow. It should be automated, and that's what this program does. So obviously you can go into more details about how to optimize the tooling path of your 3D printer, how you can minimize lost time through path optimization, layer optimization, infill optimization, and obviously going into the support structures and some of the other tools that we can use to mitigate some 3D printing issues. It's a very lengthy subject. What you need to know right now is that you create your 3D model, obviously using a design for 3D printing in mind. You export your 3D CAD model as an STL file. You slice that STL model and you generate G-code, and that G-code can be sent to a 3D printer, which will read it and automatically print your model. That's all that there is in concept. Now, let's move on for the final project of the course. So, in this project, I'd like you to take your design from the previous project, select a 3D printing technology, either fused deposition modeling, stereolithography, selective laser melting sintering, or layer object manufacturing, that you would wish to use to create your final object. And for the selected 3D printing method, I would like you to evaluate your design and identify any issues that might occur if you printed the model as it is. So if we go back to our example of the table, if we were to print this model as it is, as it is right here, we'd have issues with unsupported area underneath the table over here, which might result in the print failing. We might also suffer problems from poor contact with the build plate if we are to choose FDM. If we are to choose selective laser melting, then we might have a problem removing the metal powder from the main body of the table or from the legs. That's just an example. So I want you to choose a technology, evaluate your previous design for your selected 3D printing technology. Then I would like you, after having identified the issues, iterate your design using the methods that we have covered up to now to solve the issues that you've identified. So if we go back to our example, if I were to iterate this design, I'd say that I'd need to add a support structure over here underneath the table, or I could print my table upside down. So I'd have to reorientate the table so that it's facing this way when it's 3D printed to sort of mitigate some of the design issues. So I'd like you to iterate your design, figure out a way to solve any of the issues that you might encounter, then to present or to propose a final optimized part after the iteration process that has been designed with 3D printing in mind. So, what have we covered this week? So, we have discussed that part orientation when 3D printing is important, as it affects both the speed and the final strength of the built part. We have also covered that for overhangs of more than 45 degrees from the vertical, we would need to include support structures in our design. We have also covered that if the contact area of our part to the build plate is small, we will need to include a brim in our design in order to overcome this issue. If we include brims and support structures in our design, then we will need to post-process after our piece has been 3D printed in order to remove the support structures or the brims. We would also need to post-process if we used technology that intrinsically needs post-processing after printing, such as stereolithography or SLA, because that uses liquid resin, which needs to be subsequently washed off after printing. We have also covered that once we have our design, our 3D design, it is not enough. We need to export it in an STL format, slice it, and generate the machine code that our 3D printer can read in order to actually 3D print it. Last but not least, all that we have covered has led us to understand the 3D printing flowchart in which we create our design, from which we create our 3D CAD model in our specific file type of STL that's later sent on to be sliced by slicing software, after which we generate the G-code for the 3D printer to understand and actually print our piece. Then, depending on the 3D printing results, we can iterate in order to solve some 3D printing issues or to solve some design issues, or because we are prototyping and we are testing performance of the part and we'd like to test different designs or different iterations of our design to see how those different drafts perform. Thank you. This has been 3D printing and additive manufacturing with Ansys SpaceClaim.